you're going to go over spectral classes, luminosity, and then apparent absolute magnitude, and the Hertzsprung-Russell diagram that kind of puts all of that together. So let's go ahead and talk about, and all of these really do combine in the HR diagram, the Hertzsprung-Russell diagram. And this is kind of just setting up all the different types of planets and the different ways you can categorize them, right? So you can categorize them by their spectral class, right, which is using the absorption spectra. Then you have luminosity, which is about their brightness. And then the Hertzsprung-Russell diagram kind of ties those together. And then magnitude comes in to kind of talk about the different, types of luminosity in a way. But we'll get there when we get there. So the absorption spectra, right? We talked last episode about how different stars can emit and absorb different spectra. These are known as the spectral classes. There are 9 principal types. And the original way that these types were calculated or created is because of the way hydrogen absorption lines appear in many different stars. They appear stronger than in others. And so astronomers concluded at the time that these stars therefore had more hydrogen than other stars, and then classified them by the strength of those hydrogen lines in their spectra, with the strongest being class A and the weakest being class Q. Class Q kind of got removed at some point. And Annie J. Cannon, between 1911 and 1950, creates a modified system of this with her examination of the spectra of 225,300 stars. That's a lot of work. And this classification that she created is in use today with the classes of O, B, A, F, G, K, M, and then L and T were later added to classify dwarf stars that are cooler than M stars. And so O are the strongest, the hottest, and the T are the coolest, right? So then they had a chart about with the examples of the different spectral classes. O is Mesa or Maisa, B is Rigel, A is Sirius, F is Canopus, G is Capella, K is Arcturus, and M is Betelgeuse or Betelgeuse. I think it's Betelgeuse though. All visible stars that we see are pretty much uniform in composition, with mostly hydrogen and helium making up those stars. Cecilia Payne-Gaposchkin showed that the difference in these dark line patterns of stars are due to different surface temperatures. And so what we see is that these spectral classes then correspond to a sequence of surface temperatures, right? So the original classification was used to just determine the different spectral line types, and then Payne-Gaposchkin came along and said, actually, not only is it the spectral lines are actually also demonstrating temperature, right? So O stars are the hottest stars, and T stars are the coolest stars. And on top of this, each spectral class is then also arranged into 10 subclasses, numbered 0 to 9, 0 being the hottest, 9 being the least hot. Okay, so that's about temperature, but then there's also the brightness or the luminosity of a star. So we have apparent brightness, which is the way the stars appear in the sky from Earth, right? So the sun obviously being having the highest apparent brightness. And then luminosity is the actual amount of energy a star emits into space each second, which of course we look at as, a type of brightness, right? Luminosity is an intrinsic property to the star of a star, and it doesn't depend upon your location, whereas apparent brightness only depends upon your location. Well, not only, it's your location plus the inherent, the luminosity of the star combined. And the luminosity of other stars is reported in terms of the sun's luminosity, which is the L with the little kind of circle dot in the middle. Designating that. So the sun's luminosity is 3.86 times 10 to the 26 watts. And so then from there, we kind of use the sun as a way to calculate, to compare to different stars. So the most luminous stars are over 1 million times as luminous as the sun. And then the dimmest ones are less than 0.0001 times the luminosity of the sun. So it seems like our sun's kind of right in the middle almost in a way. They bring up the star Deneb, which is in the constellation Cygnus. It is 60,000 more times luminous than the sun. But because it is so distant, it appears less bright than most other stars in the sky. And so a star's apparent brightness depends on both its luminosity and the distance between the star and the observer in an inverse square relationship. So the apparent brightness is equal to the luminosity divided by the distance squared times 4 pi, right? And so the reason that this is that because since light spreads out uniformly in all directions, the amount of starlight shining on a unit area falls off in a 1 over distance squared from the star, right? So the example that they bring up is that if the sun was located 100,000 times further away from us, it would appear 10 billion times fainter, right? So if it was 2 times away from it, right, two times more distant, it would appear 4 times fainter, right? Apparent and absolute magnitude. So apparent magnitude is a measure of how bright a star appears to an observer on Earth. And this magnitude scale is invented by our old friend Hipparchus around 150 BCE, who is the same astronomer who measured the distance to the moon. He ranked the stars just by their terms of brightness, 1 the brightest, 6 the faintest. And the modern astronomy has kind of just taken this system and ran with it. The first modern magnitude scale defined a first magnitude star to be 100 times brighter than a 6th magnitude star, right? And so because it's magnitudinal, right, in terms of that, right, 100 times from 1st to 6th, right, rather than 5 times, right, that actually agrees with the way our eyes respond to the increase in the brightness of stars because of that inverse square law that we just talked about, right? Again, the further away something appears, the further away a star is, the amount of light we're going to see from it is an inverse square relationship, which means that it's going to change at a magnitude greater than the distance change, right? So when we see a linear increase in brightness, which for us is a 1 magnitude of difference, so a second to a first star, is a geometrical increase in brightness, which is the 5th root of 100 or 2.512 times brighter, right? So instead of it being, you see it, double brighter, right? You see it 2.512 times brighter when we go up the magnitudinal scale, which the 5th root of 100 idea comes from the idea that the first magnitude star is 100 times brighter than the 6th magnitude star because there are 5 magnitudes between them, right? So then you basically kind of calculate backwards, right? And so from a 6th to a 2nd magnitude star would be the 4th root of, the 2nd root of 100, which would be 10 times brighter, right? And so on and so forth. So magnitude differences between stars measure the relative brightness of the stars. And the most negative numbers actually identify the brightest objects, where the largest positive magnitude numbers identify the faintest objects. I'm still not sure exactly why this is. You just need to know that the more negative, the brighter; the more positive, the dimmer. It's opposite, right? I'm not exactly sure why that is. I'm sure I missed something in this explanation, or there's just more we need to understand there. But they're just kind of telling us here, hey, if it's negative, the more negative it gets, the brighter it is. The more positive it gets, the less brighter it is, right? Less luminous. Absolute magnitude is the measure of luminosity, right? So luminosity equals absolute magnitude. And if you could line up all the stars the same distance from Earth, you can see how they differ in their intrinsic brightness. And so astronomers define a star's absolute magnitude as the apparent magnitude that the star would have if it was observed from a standard distance of 10 parsecs. So they basically try to take every star, say, okay, what would it look like from 10 parsecs away? And then we can actually determine the actual light output of all stars based on this. Let me see if I can pull up a thing here real quick while we're talking here. Let's see here. Let's go there. Apologies for this. I meant to get this earlier, but the day has gotten away from me, as it were. Let's go here. Yeah. All right. I apologize. If a star is farther than 10 parsecs away from us, right? So that's the distance that we try to measure everything from. Its apparent magnitude is going to be bigger than its absolute magnitude in number, which means that it appears less bright than it actually is, right? So if it's greater than 10 parsecs away, its light that we see is not necessarily indicative of how bright it is, right? And it's in fact brighter, right? So Polaris, as their example, is 130 parsecs away. Its apparent magnitude is plus 2, which means that its apparent magnitude is not very bright, but its absolute magnitude, negative 3.6, is very bright, right? And I believe is the sun 0 absolute magnitude? I forget. There's a chart somewhere. I meant to put it in my notes. I know there's something that's 0. If a star is closer than 10 parsecs, then its apparent magnitude is going to be smaller numerically than its absolute magnitude, which of course that it appears brighter than it actually is. Sirius, for example, the brightest star in the northern hemisphere's night sky is 2.6 parsecs away. So it's less than 10 parsecs. So because of that, its apparent magnitude of -1.4 makes it look brighter than it actually is, because its absolute magnitude is +1.5. So Sirius looks brighter than Polaris, right? But Polaris is actually brighter than Sirius. Okay. And then finally, we have the Hertzsprung-Russell diagram that kind of puts this all together. So we see two astronomers in the early 20th century independently discover this relationship between the luminosity and temperatures of stars, Henry Russell and Einar Hertzsprung, and the Hertzsprung-Russell diagram is a plot of luminosity versus temperature for a group of stars. And that's actually what I was trying to pull up here to kind of give you guys a good look at. Here, I think a better version of this, frankly, than what's in the book, right? Because you can see the white dwarf, supergiants, and giants, and then you have the main sequence, right? But we'll come back to that when we need to come back to that. Let's get back over. So what we see here is that so the kind of expectation of astronomers is that it's going to be kind of random, right? That these stars were going to show up all over the chart. Right, but what it turns out is that actually there is a pretty uniform distribution of most types of stars, right? As we can see here in what is called the main sequence. Gosh. Okay. And so most stars are confined to this well-defined band, again called the main sequence. The top left shows high temperature and high luminosity stars, and the bottom right shows low temperature, low luminosity stars. So again, if we take a look at this, right, we have low temperature and low luminosity stars right here, luminosity and surface temperature, right? And then over here, we have very high surface temperature and high luminosity, such as, looks like we have Beta Centauri maybe. Over here, we have Proxima Centauri, right? One of the closest star to us is quite small and quite small in temperature, or low in temperature and low in luminosity. Right. What this means then is that there's a meaningful connection between a star's luminosity and its temperature. Cool stars tend to be less luminous. Hot stars tend to be more luminous, and this makes sense, right? But what we're seeing with the HR diagram is that's just like confirming this thing that seems reasonable. The main band of stars, as we talked about, is known as the main sequence, which is 90% of all stars. In the lower right corner, we see the red dwarfs, right? So Proxima Centauri being a red dwarf, right? DX Cancri, Wolf 359, Barnard star, Ross, etc., right? Giants, however, are off the main sequence in the upper right corner of the HR diagram. They are cool, but they are luminous, which means they have to be larger in size than the main sequence stars, right? So this is why they're more luminous than they probably should be, right, based on their temperature. So their temperature, right here, shows that they should probably be somewhere around here in terms of luminosity, but because of their size, right, where they are more luminous, right? Same thing goes with the supergiants up here. Again, if you line up their temperature, these Betelgeuse and Antares should be somewhere here near Cygni in terms of their luminosity, but instead they're all the way up here at the highest luminosity. A giant star has a radius between 10 and 100 times that of the sun. Stars with 100 to 1,000 times that of the sun are what are called supergiants, and again, those are even more luminous than giants. And in the lower left corner of the HR diagram are white dwarfs, which are sized at high temperatures but low luminosities, again, due to their size, right? So Procyon and Sirius are very hot, right, but their luminosity doesn't match because they are so small, okay? And I think that's going to do it for this video. That is kind of the, measuring stars, measuring their luminosity and temperature, and how those are related. Thank you guys so much for watching this video, and I will see you in the next one.